Okay, good afternoon, everyone. So today we'll discuss response spectra. Right. So where do we see response spectra? Balikan natin yung NSCP. But this one is the design response spectra. Yan. So this one is the design response spectra. Design. Because, well, it's based from the code. Response spectra. Okay, so it's a plot of the spectral acceleration versus the period. Okay, so basically, if you know the period of your structure, say, let's say 5-story, and ano yung rule of thumb natin, around 0.5, okay, 0.5 from the formula 0.1 times the number of floors, okay, so that's our T is approximately yan, no? 0.1 N. No? So a 5-story could be around 0.5 seconds. Yan. So kung hanapin natin dito, let's say this is 0.5 seconds. So that will give you our spectral acceleration. Okay. Okay, and also meron akong pinakita before sample response spectra dito yan. Oops. Yan, international lateral lobes. Yan, this one. Yan, no? And okay. So for example, your site is 10 kilometers no, away from the fault line no, na type A, and the soil type is a stiff soil profile SD, and under zone 4 no, so except Palawan and Sulu Tawi-Tawi, that's zone 2. So this will be your response spectra. Okay, so you will see, so if you have a 0.5 second structure, which is around 5-story, you know, approximately 0.5 seconds. So here, so that means that 5-story building, when subjected to a 0.4 G, no, 0.4 G, 0.4 G ground motion, no, ground motion, it can experience as much as 1.1 G, no, na spectral acceleration. Okay, so kumbaga kung may sensor tayo sa roof, it can measure 1.1 G. So ganun kataas, no, because it's a relatively low period structure, no? And as you saw sa video last time, no, pag high frequency yung ground motion, mas nagre-resonate sa low-rise building, no? So kaya mataas din yung nagiging spectral acceleration ng ating building. So can imagine, no, ganyan kataas, kalakas, no, 1.1 G yung pwede ma-experience, right? So, yeah. So that's for 0.4G. Okay. But of course, in reality, no, most of the earthquakes that happens, no, or we can say, no, every day, no, na may shaking, hindi naman 0.4G, no, yung na-experience ng structure natin, no. Uh, like this, yung recording ng pivot sa Pampanga last time, they only measured 0.2G, 0.2G. Okay, so therefore, by analogy, no, so your structure can experience less than 1.1 G. Okay. However, no, this response spectra is what we call the elastic response spectra. So the assumption is that our structure behaves elastically. Okay. O, even yung Abra earthquake, no, Abra earthquake, ang measurement din ng pivots is also 0.2G. No? Ito din, no? 0.2G. Abra earthquake. Okay. And also Pampanga. Dun sa station nila. No? So most likely, dun sa near the epicenter, wherein, I don't know, wala sigurong sensor or near the epicenter, baka ang na-experience is 0.4G. No? So we don't have data of that. No? So si pivots lang makakasagot niya, no? And other private building owner na possible na may sensor. No? Okay? But officially, ito lang yata yung na-measure ni pivots, no? 0.2G. Yun pa lang yung nasa presentation nila, no? Last ASEP seminar, 0.2G. But according to their simulation, the epicenter could experience, no, 0.4G din. Okay. Pero walang recordings na pinublish pa, as far as I know. So how does the code come up with this? So yun yung i-discuss natin. Okay? And this one is a numerical methods approach, because as you notice, no, we only have solution, differential equation solution, analytical, if the vibration is harmonic, no, or can be solved mathematically, no. But however, like a ground motion, no, it is not a harmonic motion, no. So very erratic siya, no. So therefore, we need an approach like a numerical methods to solve the response of our structure. Okay. I think, yeah, so in our spreadsheet, we'll be using central difference, no? Central difference method. Yung last time sinolve natin, Newmark's beta, no? So therefore, you can also use Newmark's beta method here. Although na-prepare ko yata central difference. Okay. Okay. But before that, no, let's discuss the equation of motion again. Okay. Equation of motion. Dito yan eh. Okay, so this one, no? So if this is our equation of motion, mu double dot plus cu dot plus ku equals a force as a function of time. Now, in our case, it's a ground motion. So, di ba, force is mass times acceleration. No? So, force is mass times instead of acceleration, the ground motion acceleration. We call that G double dot. Yan. So, meaning acceleration due to ground. Okay. Now, let's divide both sides by m. So, divide both sides by m. Ayan. So, makakancel out ito. And this one. So, yung matitira is u double dot plus c over m u dot plus k over m u equals g double dot. Yeah, no. Now, what is this? Now, remember, the formula of frequency is the square root of k over m. So that means this is omega square u. Okay. And what is this? So if you remember the formula of damping ratio is C over 2 omega m. Tama ba? Yeah, I think that's it. C over m to omega. So transpose lang naman to. Okay? Okay. So that's it. And plugging in this and this, so madiderive natin to. Okay? So which means that for a system at single degree of freedom system subjected to ground motion, no, the response is a function of the damping ratio and the frequency. Yun lang yung involved, no? Nakita nyo? Okay? Because syempre, if you, and of course, yung ground motion, no? Yung ground motion na data. Okay? So, kung alam natin yung frequency of our system, which is a function of mass and stiffness, and with a corresponding damping ratio, okay, you can technically find the response of this SDOF system. Okay, so you have a mass, and then you have a stiffness, which contributes to the natural frequency and a specified damping ratio. So we can determine the displacement, and of course, the velocity and the acceleration, okay, from a given ground motion. Okay, so ganun lang. No? Okay, so but again, so our typical ground motion is a very irregular motion, no? So we need a numerical methods approach. So punta ngayon tayo dito. Yeah. Okay. So let's say, remember, this is our typical ground motion recording from our sensor. Okay. Then let's zoom in, no, as a typical curve of that. So ito siya. Clear. Yeah. So let's say we have that. Okay. Now, so this is a So this is a displacement versus time curve. Okay. So anyway, this is just a derivation of the velocity. No, so from calculus, no, remember, um, when u is given, no, so to get the velocity, simply find the derivative of du dt. Okay. Okay, so the velocity is basically first derivative, no, of u or displacement with respect to time. Okay. And then acceleration is the first derivative of velocity with respect to time, or therefore this is d squared u over dt squared. Okay. Okay. So kung given yung displacement versus time curve, di ba? So just get the rise over run, no, nung curve na yon, yun na yung value ng velocity. Okay? And then if syempre kung continuous yung curve mo, no? Continuous din yung value ng velocity mo, no, through time, no? And then you will be able to plot also a velocity time curve, no? And then same process, di ba? Get the rise over run, no, value, or basically the area, no, kasi nga curve na siya, no? Then that's your acceleration naman. Okay? So from basic calculus. Okay? So ganun din yung gagawin natin dito. So given sa atin yung displacement time curve, okay, so say this is a delta t, ito, this one is delta t, and this is u sub I, this portion here is u sub I. So kung u sub I yan, therefore this is t sub I, right? Na ano kasi. So if this is u sub I, so corresponding to that is t sub I. And then on the next time step, we call this ui plus 1. So corresponding to that is ti plus 1. While this one is ui minus 1. Then corresponding to that is ti minus 1. Okay. So delta t is this one. Okay. Okay, so so the velocity, no, at ui, no, or a location at t sub I, no, the velocity there is simply ui plus 1 is 1 minus ui minus 1. Okay? Divided by 2 delta t because na-cover niyang distance is dalawang delta t, right? So this is correct. So na-establish natin yan. So the velocity there is ui plus 1 minus ui minus 1 divided by 2 delta t. So that is our rise over run, no, the slope, no, or first derivative, no, the slope ui plus 1 minus ui minus 1. So that's the rise, then the run is 2 delta t. Okay. So that is our ui dot or velocity at t sub I. Okay. Then so if nakuha na natin yung value niyon, then we can now come up with the acceleration naman, no? Kasi meron na tayong velocity. Okay? So for the acceleration, instead of ui plus 1, so ginamit lang dito is ui plus 1 half minus ui minus 1 half over delta t. No? So, dito yun. Diyan yun. So, ang cover lang niya is delta t. Okay? So, correct. Okay? But, as you see, ui plus 1 half that. So, meaning the velocity at this location. Okay? So, therefore, let's find the value of velocity there. No? So, ui plus 1 minus u sub I over delta t. So, ito lang yun. So, ito yung na-cover niya, na area. Okay? So, ui plus 1 minus u sub I over delta t. Pwede bang baguhin yung kulay nito? So, dahil kinukuha natin yung velocity here, so ang cover naman niya is ito. Yan, yung green naman. So, ui plus 1 minus u sub I over delta t. Okay, syempre, this one is also delta t. Okay, so that's the velocity there. Then how about the velocity at ui minus 1 half? So, bayin ko naman yung color. Let's make it blue. So, ito naman yung velocity at ui minus 1 half. So, ito naman yung cover. Right? And that is also delta t. So, this one. So, ui minus 1 over delta t. So, pinapagitnaan lang naman nila. Okay? And then, of course, algebra na lang, no? Algebra, manipulate that, simplify, you will derive this. Okay? So, that's the acceleration, no? At u sub I. Okay? So, we're able to derive the formula for the velocity at u sub I, and then the acceleration at u sub I, no? Yun yung gagamitin natin for our numerical methods. Okay? Because, again, so di ba, from the formula mu double dot plus cu dot plus ku. So, we will be using this u double dot formula and then the u dot formula to our equation of motion. Okay? So that's the central difference method. From the word central, no? Kumbaga, pinapagitnaan lang natin yung center. Okay? So to derive the corresponding velocity and acceleration. Okay? Sige. So I'll give you time to check that. Okay, so let's now proceed dito sa, yan. So this is a snippet from Chopra, no? Chapter 5 na. Okay. Yeah. So after plugging in the formulas, right? Yeah. Then combine common terms. So syempre i-distribute natin yung M sa bawat terms na yan and also the C. And so ito na siya. So for example, M times UI plus 1 over delta T squared, this one. Okay. M times 2UI over delta T squared. So I make it red. Okay. And M times UI minus 1 over delta T squared. So green naman siya. So the colors corresponding to ano. So yung blue is UI plus 1. The red is UI. Then the green is UI minus 1. Okay. So here, C times UI plus 1. So blue over 2 delta T. C times UI minus 1. So green. And this one, KUI. So meaning red. Okay. Then combine. So you'll have this. So in-extract natin yung mga yung multiply sa UI plus 1, UI minus 1, and then U sub I. Now we will now express this whole term here as K hat. This whole term here as P hat. So such that we can simplify this long equation as K hat UI plus 1 equal to PI hat, which brings back to ano, no, to a general formula natin ng stiffness method, no, or P equals KU, no, which you encounter sa matrix analysis, okay, of structures. Okay, and yeah, so yan yung mga constant natin. So K hat and P hat. Okay. K hat is constant, no, kasi if you notice yung ano niya, yung mga variables niya, mass is given, no, sa problem. C is also given, no, in order to have the damping ratio. Delta T is also given, no, as a analyst, ikaw magdidictate niyan, no, or kung ano yung delta T nung ground motion, no, so dyan din possible mag-depend. So basically this is already known, yung K hat at the beginning of the problem, no. What about P hat? Yan. So okay, yeah. So constant naman tong mga nasa bracket. Yan. So ito naman ngayon yung oops. What happened? Na-close ko, wait lang. Bakit nag-close? Okay, so this is the algorithm. central difference method. Okay, so initial calculation, u double dot, so okay, and then u minus 1, and yan, may note na ako dito na constant itong mga to, the k hat, a, and b. Okay, and then the calculation for each time step, this one. So therefore, each time step, kukunin natin yung corresponding displacement, no? ui plus 1. No? Because after mo makuha yung p hat per time step and k hat, which is constant, no? Saka natin makukuha yung u per time step, no? Per iteration. No? Okay. So that means ang nagdidictate ng displacement or response, no, is the p hat, no, because dependent siya sa pi, no, sa yung pi, which is basically the force, no. Force is yung from the ground motion times the mass of the system. Okay, kasi itong a and b are constant, no. And then yun nga, yung ui is also computed every time step. Okay, but yeah, the k hat is basically constant, no? Kasi yan yung ano, yan yung stiffness mo no? And again, yun nga, no? Nakikita nyo dito sa algorithm niya na k hat, no, in this case is constant, or the stiffness in general is constant. So meaning nasa elastic stage yung ating system or structure. So, kumbaga kahit anong ibato nating ground motion, it will remain elastic, no? So, nandun nila yung catch doon, no, na hindi siya realistic in the sense na na elastic, because as we know, no, in a high magnitude earthquake, no, may possible of cracking, no? So may possible of inelasticity, no, sa structure natin. So however, syempre, bago tayo mag-proceed sa inelastic stage, alamin muna natin yung elastic response, no? So this is what we're doing now. So as implemented sa spreadsheet, so ito siya. Okay. Oops. Double check lang natin yung kanyang algorithm if na susunod, no? So we have time and acceleration. Okay. So where is k hat? So makita nyo yung k hat, as I said, is constant. No, it's a constant. Okay. So, of course, the delta U is changing, and itong UI na yan is, I think, ano yan? Yeah, ito nga, yung UI na. Then, UI plus 1 is basically, mga to, P over K. Okay. Mas maganda kung i-open natin yung Excel. Okay, so yeah. P, ito pala, P over K. That's it. Okay, P over K. So, as you see, naka ano siya, no? Naka dollar sign, so meaning may K is constant, no? So nagbabago lang yung P. Yun nga yung P hat. While the P hat is dependent sa the constant A and B, no, as you can compute, no, and mass times acceleration. So binago ko yung para maintindihan na dependent yung P or the force sa mass and the the ground motion acceleration. Okay, and of course, yung A and B parameters. And then of course, yung velocity every time step. Okay, which is A and B. I'm sorry, ano pala, yan, yung displacement every time step. Okay. So MA, if you check on the formula is, yan, naka-multiply yung mass dun sa acceleration. Okay? And then, now if I check on my acceleration, naka-multiply naman siya sa 386.4. Yan yung constant V, no, sa English units. Kasi given na data natin ay English units, no? And yung data na na-download ko ng El Centro, so this is an El Centro earthquake, by the way, no, is in English units, no? So inch per second square. Yeah. So I use G na English. Okay. Okay, sige. So so i-send ko muna sa inyo, no. I'll give you time to open this, no, para makalikot nyo, no, ma-open, makarelate kayo doon sa mga tinuturo ko sa where's that? So, kasi as you saw sa Teams, no, that this is one of your take-home exam, no? Gagawa kayo ng response spectra. So, syempre, babaguhin ko lang yung ground motion. No? Okay, where's that? Nawala. Ay, teka. Save this first muna. Save as ko muna pala. Okay. Earthquake. Earthquake. Response spectra. So save. Okay, kasi naka-open. So that's 6.5 megabytes. Okay, sige. I'll give you time to open the file first, no, and then check. Kung may question kayo sa baka may mali akong formula na naglagay, no? So let's have a it's 4 o'clock. So let's have a quick break lang. So okay, so if you are now opening the file, so you can now check the El Centro ground motion mismo. Okay. So this is the plot of El Centro. Yeah. So pag click natin to, okay. So if you see, ito yung raw data, ibig sabihin. Saan ba? Not this. Okay, ito. So that's why I have acceleration versus time, no? then kasi yung data is naka-normalize sa G, no? So para ma-convert into acceleration, you need to multiply with the G in English units, which is 386.4. Okay? Okay. So ito pala yung naka-ano. Yeah. Naka-normalize sa G siya. Kaya you will observe that the PGA of this earthquake is about 0.3, no? So hindi siya 0.4, no? It's only 0.3, no? It's just 0.3 G. So hindi pa yan yung recommended ni NSCP, right? Because as per our NSCP, the recommended ground motion is 0.4. That's a design PGA. So na yun. Magpas ba ako? Yeah, okay. So zone 4. So meaning that's 0.4 G. Okay. Anyway, for the sake of discussion, no? So we will try to create a response spectra of that. That's why dun sa mga ano, yung mga non-linear analysis, no, ng mga firm, so nagkakaroon ng ano ng concept of scaling. Yeah. Because you cannot you cannot really get an actual ground motion in all ground motion available worldwide na lahat 0.4. Hindi naman nangyayari yun. No? So let's say merong 0.3 G. So that's why in order to comply with the code sa let's say non-linear analysis, kailangan mo siyang scale up, no? From 0.3 to 0.4. So yun, that's another topic. Okay? So may scaling na tinatawag. Ayan. So that's it. So by doing numerical methods like this, no, a central difference method approach, we can now plot. So as you see, meron tayong iteration per time step. So our delta t here is 0.02. Okay? Medyo ano pa yan, medyo what do you call this? Medyo malaki pa nga yan, no? Yung delta t na yan because yung mga available ground motion ngayon dahil digitized na yung mga sensor, no? 0.001 pa, no? Ganun sila ka-accurate. Okay? Now, this sheet is 0.5 seconds. So meaning this Excel sheet that's open right now is for let's say 5-story building, no? About 0.5 second na period. So how do I get that? So I have a mass of 2.253 and a stiffness of 39.952. So I'll get my frequency square root of k over m 12.559. Of course, period is 2 pi over the omega. So that's 0.5 seconds. Okay, the damping ratio is 0.02. Ano ba yung naki-Chopra? Okay, damping ratio is 0.02. Yeah, okay. 2% pala. Okay. So ito yung kay Chopra. Yan. So ito yung actual ground motion as per Chopra. So as you see, no, hindi siya lumagpas ng 0.4 G. So basically 0.3, okay? And it happens at what time, no? Early on, no? Mga around saan ba yung 0.3? Ito. This one is 0.31, about 2 seconds, no? 2 seconds from the actual data, no? So of course, may in real data nito malamang hindi lang 2 seconds, no? Kumbaga yung available data that I downloaded is ito yung lumabas, no? At about 2 seconds from the ground motion. Doon na record yung 0.31 G na ground motion. Ito din is about 0.29 lang. So, nandito siya. So, 2 seconds, no? So, when the earthquake happens about 1, 2, biglang lumakas yung, yung acceleration. Okay? So, and according kay Chopra, the 0.5 second structure will have a peak displacement of 2.67 inch. Yan. 2.67 is how about 3 inch is 75 mm, no? So roughly around that, no? 60 to 75, okay? 2.67 inch. Okay. So let's see using our spreadsheet. Also, by the way, no, from the recordings, no, it observed that the El Centro happens about 30 seconds to, I believe. Ayan, yan. Sumobra lang yan. Ayan. Around 31.14 seconds. So, 0 to 31 seconds, no? Then, PGA happens, no? At about 2 seconds. Then, unti-unti, nagsasubside na yung ground acceleration. Okay. So, of course, may kakaroon tayo ng data of the displacement from 0 to 31 seconds also. Okay? And then, in order to get the maximum value of our response, no, or UI plus 1, you just use max min function, no, sa Excel. As you see here, it's max min. And of course, the absolute max is, according to our result, is 2.71 inches. 2.71. Whereas Chopra gets 2.67 inch. Roughly the same. Right? Most likely sa ano lang yun, sa round of error. Okay, and when did it occur? No? So, saan yung 2.71 inch? Yan, at about 2.32 seconds. Okay, 2.32. Ito ba? 2.71 din. Yan, hindi naman. So, yun, no? 2.32. Okay, so you can now realize, no, that 5-story building, no, 0.5 second structure, PGA happens 2 seconds, no? Biglang lumakas yung ground acceleration 2 seconds, pero yung peak response, peak displacement rather, happens at a later time, no? 2.32 seconds pa. No? Mga point something seconds before nag-occur yung peak displacement. Okay? And as you notice, wala na, no? So, siya na, no? Yun na yung pinakamalaking displacement. So, mas mababa pa yung succeeding displacement. Okay, kasi as you notice naman, syempre, bumaba din yung ground acceleration. Okay? So, how about the other period? So, next, 1 second structure, no? 1 second. So, 1 second is roughly 10 story, no? Roughly 10 story. 10 story, and the maximum deformation is 5.97 inch. So, makes sense, no? Because 5 story versus 10 story na mas flexible, so mas mataas, no? So, it should have a higher displacement. Okay? 5.97, let's see, punta tayo sa 1 second here. Kaya meron akong Excel sheet here for 1 second, or basically 10 story. And using max min function, I got 6 inch. 6 inch here as the maximum displacement. 5.97, 6 inches, roughly the same, no? And when did it happen? Okay. Ito, 4.8 seconds. 4.8. Okay, and nakita nyo, no, kung i-compare nyo yung vibration, no, or yung plot nung peak displacements. Okay? Can you observe that? So si 0.5 seconds, yeah, so medyo dikit-dikit yung ano niya, no, uh, yung ano natin, no, yung plot natin, no. Pagdating sa 1 second, medyo layo-layo na. Kita nyo? No? Okay? Kasi mas mataas na yung period natin, no? Mas mataas na, 1 second na. So therefore, and also, yung kung kailan nag-appear yung maximum displacement, 4 seconds. Unlike si 5-story building, no, happens 2.32 seconds. Nag-occur yung maximum displacement niya. Si 10-story building, nag-occur pa nung about 5 seconds na. Mas malaki yung lag, no? Okay? Ito niyo, no, so here you will realize, no, kumbaga we are able to show in numbers, no, yung phenomena na nasa video last time about resonance, no, na yung high speed na ground motion, no, nagre-resonate siya or high acceleration ground motion, nagre-resonate siya sa low-rise building, no? 2 seconds PGA and 2.32 seconds yung ano niya, yung peak din niya. Okay? Itong ating 1-story building, 1 second or 10-story building, at a later time pa siya, no? Or 4 seconds or about 5 seconds nag-occur yung peak displacement. And how about 20-story, no? Twice the height, they say twice the height, no? And according kay Chopra, 2 seconds, 7.47 inch. Of course, mas malaki, no? Mas malaki yung kanyang displacement, okay? And nag-occur yung kanyang maximum deformation more than 10 seconds, no? Let's see with our spreadsheet, 20-second or 2-second or 20-story building, 7.47 inch, no? And it should happen more than 10 seconds. Okay? Okay, so you can see the yung plot of yung cyclic motion niya, no? So mas malaki yung period niya kasi. Okay? And so on and so forth, and until you plot you combine all those plot, no, of maximum response, no, peak deformation response, you will come up with this curve. So we call this the deformation response, no? Deformation response. Deformation yan. Okay? So ano nga yung first derivative ng deformation? Velocity naman. And then second derivative of deformation, acceleration naman. Okay? So the trend is as your building goes higher, so meaning the period goes higher, so therefore the deformation also increases. So it's obvious, no? That's what we observed, and we were able to prove that mathematically using numerical methods approach. Okay, so okay. Okay, so we're done with the deformation response, no? And next is the velocity and acceleration. And it turns out that in order to plot the velocity and acceleration, we're just going to multiply by omega. No? So ito yung na relationship. In order to plot the velocity, multiply the deformation by omega. No? And then the acceleration is omega square times deformation. Okay? Kaya this one, multiply by omega, you will get this. This by omega, you will get this. And this by omega, you will get this. Omega is the frequency, no? And then omega square times this, you will plot this, this times omega square, this, and so on and so forth. So this is now our velocity response spectra. And then this one is the acceleration response spectra. So basically, importante talaga yung deformation. And after getting the deformation, multiply each of that value by omega or omega square to plot the acceleration response spectra. Okay? And this is the result, right? So you will see that for this one, no? Paano ba ito? I-drawing ko. No? So ito yung acceleration response spectra. No? So if I smoothen that curve, I can generate something like this. Diba? Which is what? This is familiar to you, no? So this is our basically the NSCP response spectra. Okay, so if I open our NSCP response spectra, yeah, diba? Okay, so pag ano, syempre in-smoothen na lang sa code. Okay, and of course this one. Okay, so that's the acceleration response and spectra. Okay, and if you click on the values, yeah, so you will notice that acceleration, no? Remember, no? This El Centro ground motion is only 0.3 G, no? 0.3 G, no? So saan nga ba nangyari El Centro? So let's search for that, no? Open ko lang si El Centro ground motion. Ay, sorry. El Centro earthquake. Ito, yan. Vibration. So, kung wala kayong data, no, kung gusto nyo makuha yung raw data rin talaga, so, yeah, you can search on this website, vibrationdata.com. So, yung recordings niya, span spec. So, it happens, so yeah, sa US siya. Imperial Valley. No? Ay, hindi, sorry. Yeah, 1940 pa pala to. Tama ba? Yeah, okay. Yan. So yan yung destruction sa sa caused by this Centro earthquake. Yeah, May 18, 1940. Kaya yung delta T niya 0.02 pa. No, medyo medyo malaki-laki pa yung delta T niya. Unlike ngayon, mga digitized na yung mga sensor, mas precise, mas maliit yung delta T natin. In your case, no, as for your machine problem, yung Pampanga earthquake, no? So nandun siya sa G drive. Bibigay ko pala kayo yung link ng G drive, no? Meron na siyang may data ako na nakuha from PVOLs. So gagawan niyo 'yon ng response spectra. Okay? So again, 0.3G lang si El Centro, but you will notice that the spectral acceleration that you will derive is more than 1G. No? In fact, ito nga, almost 1.1G ito. Okay? 1.09G, which is almost the same na rin dito sa response spectra natin sa as per code base, no? 1.1G. Take note, this is already 0.4G na ground motion. So 0.3, 0.4, no? Ibig sabihin, halos hindi naman nagkakalayo, no? Okay? So that's the spectral acceleration. So meaning, yan yung acceleration on top, no, of your structure. Okay? So in short, referring to this response spectra curve, our structure 0 to siguro nito mga 0.2 to 0.5 second structure, or 2-story to 5-story building, no? By approximation, can experience as much as 1.1G na spectral acceleration, which is consistent do sa video last time, no? Yung sa ngayon. Okay. Type natin dito, resonant earthquake. Sabi yung building. Okay. YouTube. Building resonance. This one, right? Palipasin ko lang yung ads.
When we see this kind of picture, it's we can make this expression nothing appears because the eccentric is not far from the axe. So now I am putting this far, and now I see the beginning of the working, this system working. So now I'm going to study the resonance.
So as you will see,
we can see that the big buildings resonates. I'm increasing the speed. And now, yes, the big building, and now the intermediate building resonates.
Will resonate the mid-rise, no? And then yung fastest speed will resonate dun sa low-rise building. Okay? So that's it, no? We were able to prove that phenomena, no, in numbers here. Okay? So well, with this ground motion from El Centro, no? So yung malakas niyang acceleration, no, will resonate, no, with the low-rise building, no, such that it can experience as much as 1.1G pa nga na acceleration, spectral acceleration. Okay, that's the spectral acceleration, which is consistent with so ngayon natin, where is our eta. Yung from pivots, no? So let me check, no? EQ2. Spectral acceleration map of the Philippines. Yan. Copy ko lang muna. Yeah, pwede ko rin pala i-send sa inyo kasi nga earthquake and engineering tayo. No? I don't know kung kakasya. Ay, malaki pala. 120 megabytes, no? So, yeah, pa-open na lang. Earthquake. Yeah, this one. Yeah, can you see now yung spectral acceleration map of the Philippines? Okay. So, maximum considered earthquake using probabilistic seismic hazard analysis. Ano ko na to eh. Na bullet ko na to. Bookmark ko na pala to. So for example, sa NCR, yan. So spectral acceleration map of NCR for 0.2 seconds period. No? 0.2 seconds period. So basically, two-story. No? Two-story building, no? Approximately on a rock site. No? Pero yung earthquake mo is MCE, no? Yun yung nakalagay sa sa title. MCE meaning maximum considered earthquake. Na ang return period is 2,475. So ganun kataas, no? Ano yan, mga more than 0.4 G pa yan, malamang, no? And yeah, so as you will see, yung red or highest spectral acceleration is 1.7 pa. 1.7. Eh, yung nakukuha lang natin ni kay Chopra, 1.1 G only. No? Siya, 1.7. Kasi nga, MC ito. So, which is most likely more than 0.4 G pa yan, for sure. No? Let's say, sa Valenzuela, 1.2 G. For two-story building, 1.2 G. Okay? So, at least, by now, looking at this data, for me, you're now familiar. No, you can say na you can derive or you can mathematically come up this data, no, using numerical methods approach like this. Okay, because for a certain ground motion, siyempre wala lang tayong idea anong ground motion yung in-apply ni pivots dito. But for sure, having this MCE 2,475, that's more than 0.4 G, I believe. Okay? And yung if you check on the title, it's on a rock site. No, kasi earthquake happens sa rock zone, di ba? And then na-amplify na lang based sa soil on top, no? So meaning this 1.2 G will be amplified further, no? Because let's say here in Valenzuela, the soil is relatively soft, no? Relatively soft here. So ma-amplify pa tong 1.2 G. Okay? So yan, no? Ma-amplify siya but ma-reduce later because the ground motion as according to this data is MCE, no? Eh, tayo DBE ang ginagawa natin, no, sa design. DBE is from the definition this one. Design basis ground motion has a 10% chance of being exceeded in 50 years. Diba? Kaya nga, tinuro ko ba? Kaya nga, I need to, or you need to convert this into a return period. And my shortcut there is 50 divide 0.1, kasi nga 10% chance, you will roughly get 500-year return period. Okay? So yan yung basis ng design natin. And we call that DBE, Design Base Basis Earthquake. Okay? While this data is MCE. Okay? This is MCE. So from MCE, i-downgrade natin itong value into DBE. From 2,500 year return period, gagawin nating 500-year return period. Okay? Well, syempre, ginawa ito because yan yung standard. So, sa IBC, yan yung presentation din sa Amerika. Kaya kailangan nating sumabay sa international standards from IBC, International Building Code. Okay? Kaya naisipan tong gawin ng ASEP together with pivots. Okay? Yeah. So at least you're now familiar with the terminology, spectral acceleration, how to mathematically obtain that. Now from this deformation response spectrum, so ito yung plot nun. Yan, yan, okay? So ito yung data. So ito yung nakuha nating deformation from each period that kinuha lang natin yung maximum deformation. Yun yung key dyan, no? Kukunin mo yung maximum deformation, teka, balikan natin yung 0.5 natin. Bakit wala pala dito yung 0.5? Let me add 0.5 here. Dito, insert ko. Para makita nyo. So, lagyan ko siya ng period na 0.5 seconds. No? Wala din siyang 1 second. No? Insert 1 second. Yan. And then, get the response here. So, 2.7. So, punta ulit ako dito. Plot. So, equals, copying ko ito. Paste this. Sorry. So, absolute. Yan, delete ko. Then, punta ako dito sa 0.5 seconds. Then, I'll check this. Yung 2.7 na maximum deformation. Then, enter. Yan, so nandun na siya. Okay. Ayan. Then, copy-paste ko lang. Bakit ano value nito? Copy ko lang to. Ayan. And then, just copy-paste this formula. Okay. Omega times the deformation. This one is omega squared times deformation. And then how about 1 second? Copying ko muna to. Then I'll change this formula. So peak deformation, 1 second here. Ito, yung 6 inch, no? 6 inch. And then enter. Then copy paste this. Ayan. Nasama na ba siya? Yan. So, na-include na siya. So, as you see, medyo, syempre, kulang ako ng data, no? So, pinakita ko lang naman yung general trend. Okay? Yan. So, ito yung nakuha natin, the deformation response. So, as you see, at least yung trend increasing din talaga, which is consistent with this one. Okay? Then my velocity is, ito si Chopra. Ito naman yung sa atin. So if you connect this, you'll get something like this, maybe. Siyempre, kulang ako ng mga data dito, no? So, yun yung gagawin nyo. No? Siyempre, ibang earthquake nga lang, ibang ground motion. And then finally, for the acceleration, nakita nyo naman yung trend, no? Halos the same. Umangat bigla, then, so of course, if I, kasi nag-umpisa ako sa 0.1 seconds, no? So I should have started 0.0 ganyan, 0.02, 0.034, something. And then maybe I will get something like this. Okay, which is similar to this. Okay. So at least nakikita nyo no, na that's really almost 1G, 1 to 1.1G. Why? Because, di ba, our 1G is 300, 386.4, di ba? That's our G. So I'm getting here, pumalo ako ng 400 plus. Ito, 400 plus. So that's more than 1G. Okay? Which is consistent with this. Okay? And so our 0.5 second is here, 1.09. Okay? 0.5 seconds. So pumalo talaga more than 1G siya. Okay? So, and as you see, no, yung parang peak niya, no? So that's why in general low-rise building will experience maximum spectral acceleration talaga. For a ground motion na for a very high PGA, no? So low-rise building or relatively low period will experience the maximum spectral acceleration as we saw here. Okay. Okay, so let's proceed back here. And so that's for 2% damping ratio. And ano ba yung damping natin? Parang default natin is about 0.05 or 5% damping ratio. Okay. Now for a very stiff structure, no? So according kay Chopra, no? And you will observe naman, no, that if you have a very stiff, no, lumalabas, the acceleration will be the same, no, dun sa ground motion acceleration. For example, this is a 0.02 second structure, very stiff, no? The ground motion has a, which is 0.32 G, no? And by simulation, no, by numerical methods, no, you will come up with a spectral acceleration of 0.32 G also. Nagtutugma sila, no? Nagde-design, no? Kasi very stiff siya, no? Sumasabay na siya, no? Sumasabay na siya sa ground. Okay? So actually we call that pseudo acceleration, by the way, no? Pseudo acceleration, because it's pseudo means not realistic, no, or not true, no, because this is theoretical, no, this is theoretical, no? And as I said, no, early on, that we're designing for the NSCP is expecting our structure to really behave inelastically, no, not elastically, no, during earthquake. Okay, so and as I said, this is an elastic response spectra. Okay, so kung yung stiffness natin is really constant, no, the whole duration of the earthquake, then so so the spectral acceleration that we solve will be the same, no? Dun sa ano natin. Okay. And very obvious naman, no, na for let's say mga low PGA, no, let's say mga 0.0 ganyan, 0.02 G, no? Well, on that scenario, our structure will still behave elastically. Ibig sabihin, hindi kasi ganun kalakas yung force, no, para mag-crack yung mga columns natin and beams. And now, on the other hand, if your building is too long or having a flexible structure or very too long period structure, no, the ground deformation will equal dun sa peak deformation of your structure. Ayan, 8.4 inch yung ground deformation, while the peak deformation of the structure is 8.23 inch. So, halos nagtutugma rin sila. Okay? So, kumbaga, stationary na halos yung, ano, yung mass sa taas, no? Kasi sobrang, ano niya, so sobrang bilis nung ground motion, tapos sobrang flexible ng building, naiiwanan na siya, eh, no? Yun nangyayari. Okay, so that's it for our response spectra. And I hope that so by now you can now okay. So you now know the derivation of this curve, of this curve, that for, let's say, a 0.4 G earthquake, you will come up with this data. Okay. So maraming factor actually, no? So yun nga, the damping ratio, no? So as you saw sa spreadsheet natin, we assume a constant 2% damping ratio. Okay? Pero hindi naman ganoon rin kalaki, no? For example, ano ba? Gawin natin siyang 0.02, no? Gawin natin 0.08. Yan. Yan. So from 2.7, yeah, naging 2 inch siya. So bumaba, no? Kasi nga lumaki naman yung damping. Okay? Lumaki naman yung damping. Okay? So 0.02, balik ko. Okay? So lumaki kasi yung damping na value mo. Okay? From 2% to 8%. So that's why so as you see, bumaba yung deformation. No, that's why one of the retrofitting approach sa mga old buildings is inserting damping material, mga dampers, no, because yeah, so basically that they reduce, no, the deformation during earthquake. Okay, kaya nga may mga yung sa Taiwan, no, they call that tuned mass damper, no. So tuned mass damper, because you can see here that mathematically, no, it reduces the damping, or sorry, the deformation of your structure. Okay. And so that dictates, no, those two parameters, no, dictates the response, no, the damping and the frequency, which is a function of mass and stiffness. Okay, so what else? Yeah, so I'll just give you the link of anyway, hindi pa naman ngayon yung deadline, no? Kaya pero giving you an advanced info sa machine problem ninyo. Okay? And yun nga, so that's for the acceleration. As you see, then habang tumataas naman yung period of the structure, ano naman yan lumalaki? The deformation. Okay? So looking at this curve, no? So the long period structure may not, no, as you saw sa curve, and as we were able to derive, no, mathematically, that long period structure, yan, 2 seconds, 20 story, and even 10 story, they tend to have low spectral acceleration. Kasi nga, nagiging flexible sila. However, sila naman tumataas yung deformation. So, kagaya nung sa case ng, say, ito nga, Pampanga earthquake. Pampanga earthquake, 2019. So, try to search on it. Well, ibang case tong Chuson Supermarket kasi ano yan eh. They call this construction issue talaga yan. Manila. Try natin kung may Manila. Walang footage sa Manila. Ayan, this one, di ba? See? So, syempre, on top, hindi naman natin nakikita yung magnitude ng displacement. But yeah, because yung malaki yung deformation dyan, no? So, such that yung pull sa taas, no? Talagang nagano siya. Ayan. Na-displace yung water sa taas. Okay? Maliit yung acceleration niya. Yes, yung spectral acceleration niya. But yung displacement sa top is mataas. Okay? So, yan yung mga damages. And of course, related to design, no? So, mapapansin nyo yung mga mid-rise to high-rise, no? So, because of this phenomena, no? Those high-rise building could have even a minimum base shear, no? Pero ang magdidictate ng design will, based on this phenomena, the drift, no? Kasi nga tumataas yung displacement. Okay? So lumalaki yung displacement ng mga high-rise building. So such that pag nag-control yung drift, syempre you will be forced to add shear wall, no, to control the drift. So para maging stiffer yung building. So increasing the stiffness will reduce the period, no, because mass and stiffness control the period. Okay? So yeah. So that's what we did is manually creating the response spectra using Excel, no? Pero in fact, kulang pa siya because I only use very small period, no? Or sorry, small data, no? And as you saw, to be able to come up with a smooth curve, no, ng response spectra or accurate curve, you need to assume more period, no? So let's say from 0.01, let's say with an increment of 0.005, no? Yan. Hanggang you reach about 4 seconds, no? So ganyan kadami. So kung i-divide natin yan, 4 seconds divided by 0.005 na increment, no? That's about 800 Excel sheet. Ayan. So ganun, no? So that's why you are free to use MATLAB, Python, or VBA, no? Pwede nyo gawin. No? So 4 divided by 0.05, 0.005, 800 data sets, no? So 800 data points ang kailangan mo. So yung ginawa ko, ano lang, 0.5, 1 second, 2 seconds, tapos mga additional 5. So ano lang yun, 10 lang. No? So at least just to show the general trend. Okay. Now, there's a software available to quickly come up with the response spectra. No, ito nga is a seismo signal. No? Sorry. I don't know kung gumagana pa yung seismo signal ko. So, of course, provided by extractors, no? Pero you can, of course, download, pero may trial na 30 days, no? Kung gusto nyo. Yan. So, you just have to open the data. Ayan. So, ito yung mga, may ano naman siya, no? May mga, ito pala, Imperial Valley. Yan. Imperial Valley. Open. Yan. So, may, 1979 naman to. Yes. For example, yan, meron na siya. So, first line, so, kung, let's say, kung makakuha kayo ng data sa pivots, to, something like that. So, anong nag-start yung first line? 1, 2, 3, 4, 5, 6. So, tama. First line is 6. Yung last line, na-detect naman niya yun, I believe, kusa. Then, time step, dt.01. Okay, correct. Acceleration column, second column, correct. The units is G. Okay, correct. Then click OK. Yeah. So, yan yung recordings niya. And PGA is 0.3G. 0.3G din. Okay, so ito yung velocity, displacement, and yeah. So, click ka lang sa elastic response spectra. And then, pili ka ng graph, period versus acceleration. No? Or pseudo acceleration, pwede. Then refresh. Okay, pili ka din ng damping values mo. 2%, 5%, refresh. So, yeah. So you will see, iba-iba ang response spectra talaga per ground motion. Okay? Iba-iba. Okay. Pero at least, no? 0.3G yun, no? So, nakita nyo naman yung general trend that still, pag ganun pa rin yung acceleration. And this is 0.9. Yan. Kung i-smoothen mo yan, siguro pag ganyan. Okay. So, 0.8. No, kasi nga, 0.3G lang naman to. And also, depending din kung saan kung nasan yung recording sensor. Kung nasa malambot na lupa ba siya or very hard rock. So, yun yung mga factors na yan. Okay. Okay, but at least the trend is the low rise or low period structure will generally have the peak spectral acceleration. Okay. So when I click pseudo acceleration, I believe walang nagbago, no? Kasi acceleration, pseudo acceleration. Okay. Alas wala naman nagbago. Now, for this period versus displacement, check natin. So, the general trend is still the same, no? Habang tumataas yung period, nag-increase yung displacement. Okay? So, that's one quick way of generating the response spectra. So, syempre, dahil ako gusto ko yung pahirapan, yan. So, I wanted you to create this in, syempre, binigyan ko na nga kayo ng spreadsheet ko no? So, at least, modify the ground motion, then try to do additional Excel sheet for different period in order to produce a plot na mas maganda dito. That will still resemble an output like this. Okay? So, pwede nyo namang i-compare, no, with this, no? So, right away, you can determine kung tama yung ginawa nyo na response spectra because you have a software like this to verify if correct yung response spectra. Okay, question?
Sir,
Anyway, malayo pa. Malayo pa naman yung deadline, no?
Sir, pwede, may tanong na ako. Sir, for example, nakagawa kami ng maraming, na-plot namin yung mga response with regards to different periods. Paano namin siya parang gagawing isang file, isang plotting lang. So, parang ganun.
Ito, nasa isang file lang siya. Kumbaga, iaano nyo, yan, ginawa ko is, nag-come up ako ng isang, what do you call this? Parang table, no? Yan, naka-ano lang siya, naka-reference lang. Hinuhugot ko kada, kada absolute max, no? Yan. Although, parang old school approach, so, kasi ang habol ko lang naman is to show the the values, no. Pwede nyo i-VBA, yung iba nag-VBA, no, nag-visual. Sabi ko nga pwede rin kayo mag-MATLAB, no, or Python. Pwede niyo gawin yun. Nasagot ko ba? So, ganun lang naman. No? Kasi once na nalagay mo siya into one column, 'di ba, sa Excel, plot, no? Gawan mo lang kagad ng insert plot. Tapos yung period versus deformation na data. So you come up deformation response. Tapos another plot for velocity. So velocity response. Then another plot for acceleration. Okay. Okay, so no more questions ba? Let me check lang. As I said before, no, when studying MDOF, no, we will still be using the concept of SDOF. No, yun nga. After getting the each modal period, no. So each modal period, of course, will have its corresponding responses, no? So ang nangyayari sa MDOF is we will convert that into a single degree of freedom problem, but isusuperimpose natin lahat ng mga responses ng SDOF. Yan. Kaya ganun din sa earthquake, no? Let's say 5-story building. Magda-dynamic analysis tayo, for example, no? Ang that multi-level building has say 5 modes. So in order to get the total response of our 5-story building, we will superimpose the responses of 5 modes. Yan. So kaya kailangan alam natin yung response of each mode, no, to a certain ground motion. And this response spectra topic is very important, no. So kumbaga kung meron ka ng established responses of bawat SDOF structure, no, say halimbawa ang modes ng 5-story mo 0.5 seconds, 1 second, 2 seconds, something like that, no. Kukunin mo ngayon yung responses nung 0.5, 1 second, 2 seconds na yon doon sa corresponding earthquake ground motion. Then co-combine mo lang yun. So ganun lang, no? Ganun lang yung nangyayari sa dynamic analysis, okay, or response spectra analysis. Okay? Yan. Kaya at least if you have established responses, no, hihuhugutin lang natin dito yan. Okay. Yun yung nangyayari. Okay, so that's it. And anyway, the deadline is ano pa naman, way too far pa naman. So you have a lot of time to do now your machine problem. Pwede niyo nang kalikutin yung Excel sheet. Okay, then okay, see you next week. Okay? And I'll just upload na lang the recordings later.
Thank you, sir.